thinking and scheduling, especially the bridge between the two views of scheduling coming from the worst case analysis and the traditional queuing theory. We'll have two speakers. So the first half will be delivered by Nikhil Bansal from University of Eindhoven.
Okay, thanks, Varun. Yeah, so this will be a joint talk between Adam and myself. And I should say up front that this will not be maybe similar or like a traditional tutorials we have been seeing before, because it's not really that there are too many connections yet, and maybe one of the hope of this semester is that there will be at the end. So we'll basically just be giving a few connections and some glimpses of things that we know might be related. So let's begin. So what is online scheduling? I mean, we have all seen it in some form or the other. So typically the setting is you have, say, one server or a collection of servers, and you have some tasks that are coming maybe over time and need to be done. And so this is the scheduling setting, and you are interested in sort of optimizing some objective. And again, there is a whole collection of objectives, waiting time or fairness, throughput, and so on. You might have various constraints, jobs can be preempted or not, migrated or not, and so on. There might be deadlines. And you could have sort of various settings, single machine, multiple machine, networks. So you could have this whole matrix of all kinds of possibilities and scheduling. And again, there are various communities look at these things because they're sort of important in resource allocation and so on. So we'll be focusing on sort of two extremes in some sense. And again, I'll define these later on. So one is the comparative analysis, which most of us have seen, where the focus is sort of you want to design an algorithm and compare it to what's the best possible you could have done in hindsight, right? So you typically compare yourself to the best possible thing. And in queuing, it's the opposite contrast. You don't want a relative guarantee. You usually want some absolute guarantee. So you fix, okay, here is a particular algorithm. Here is maybe input workload. And what's the exact or approximate expression I can get? So that's sort of one difference. The second difference is, again, here the focus is on worst case inputs. Like really those determine everything. In queuing, it's very important to make your model precise. What's the precise stochastic model? And then you prove certain guarantees. And again, comparative analysis, since your focus is on worst case, you typically come up with sort of a robust algorithm that for any input will do well or not. And in queuing, typically, your analysis or the algorithm is optimized to a certain workload. Right? So maybe this is a nice picture. So suppose you have this input space of all possible instances. So in comparative analysis, all the focus is here, right? So these are some bad instances. And the whole algorithm design, everything is sort of, so these determine everything. And in queuing, typically you would partition your space into, or not a partition, but say look at the part where things are nicely behaved, maybe different distributions, and maybe try to give a more nuanced view for each of these, how well you can do and so on. Right? So again, these kind of seem poles apart. And one of the goals of this tutorial is, can we still use insights from one area into the other? Right? And in particular, design good algorithms that maybe combine benefits of both of these ways of looking at things. Okay, so that's sort of the plan. Okay, so again, so I'll begin with maybe defining the basic terminology, especially in the queuing, because probably not many people are familiar with sort of queuing models and the basic way to view things and techniques. So I'll spend maybe quite some time here trying to build intuition. And then we'll look at one particular case study of minimizing flow time. So flow time is, again, I'll define this formally, but it's a metric very well studied in scheduling. And queuing people probably know this as response time or sojourn time. And it has various names. And again, we'll see sort of how ideas from one field can help the other. And towards the end of the talk, I'll highlight some other possible directions where I feel there could be some more future work. And then Adam will talk of many more connections in the second part. Okay, so quickly, what is comparative analysis? Again, we all know this. So in the scheduling setting, we should think of it as jobs arrive over time. And the algorithm has no knowledge of future arrivals, right? And it should make its decisions based on current knowledge. So more concretely, say you have some jobs 1 through n coming over time. Maybe a job has a size and arrival time. And okay, and we'll look at the most simplest setting where there is just one machine, so on. And you want to sort of find a schedule that minimizes some objective, right? And you can put anything in this x, y, z. So again, in the online setting, at time t, you only know things that have arrived by time t, right? Whose release time is before time t. And you create a schedule on the fly, and you cannot undo past decisions, right? Good. So interestingly, already here, you could define sort of two variants in this thing. You can have a stricter setting of So what it means to be online, and this setting is called non-clairvoyant or blind setting, and we'll look at this quite a bit later on. So here, so this is a stricter setting. So when a job arrives, you don't know its size, right? Like how long it will take to finish. So all you know is, okay, there is this job in the system. You maybe keep working on it, and at one day it announces, okay, I've completed my service requirement, and then it leaves. Right? So this could be a stronger notion of online. Right. So can we still design good algorithms here? Okay. So by the way, if there are any questions, just feel free to ask. And again, we, as I said, compare the sort of look at all possible inputs and look at this ratio of how good your algorithm does versus the offline best, right? Or how well you could do in hindsight. And typically in competitive analysis, the sort of, if you have any problem, the holy grail sort of is to, find the right competitive ratio. There is sort of one right answer. And typically you try to chip away from both sides. Maybe you try to sort of successfully improve lower bounds that how well any algorithm can do. And typically this involves constructing clever strategies, adversarial strategies for instances. And on the other side, you sort of try to design better and better algorithms and maybe smarter analysis. Right? So again, we all know this. So let's look at the queuing models, which probably, not many people know. So the most basic, the first thing you study in any queuing course is what's called the MM1 model. So M means for Markovian. And so the first M is for the arrivals, and we'll see what this means. The second M is for the job size distribution. And this one is for a single machine setting, right? So the picture here is that, okay, you have some server, and sort of jobs are coming at some rate lambda. Now, what does this mean? So this M here means that jobs have a Poisson distribution with rate lambda. And again, to remind you, if you haven't seen this in a while, so a Poisson distribution you should think of as, if I look at any infinitesimal interval of time, say between t and t plus dt, it's like the chance of this job showing up is lambda times dt, right? So it's literally the rate. And if you're used to more discrete settings, you can think of as the geometric distribution, like every time there is a coin toss, and with lambda probability, this job shows up. Okay. So again, it's probably well known, everybody has seen this, that if you have Poisson arrivals, it really means that between any two arrivals, the distribution is geometrically distributed, or exponentially distributed, sorry, and the mean is 1 over lambda. Right? So this is same as like if you're tossing coins which are heads with probability p, you expect about 1 over p steps until between consecutive heads. Now similarly, for the service thing, there is a distribution. So jobs have this size, which is Poisson with rate mu, or the service rate of this. Okay, so typically in the queuing world, it says that, so this server can finish jobs at rate mu, which means if you're working on a current job, it could just end like in this small interval with mu times dt probability, right? So it's again sort of exponential. And again, so Poisson at rate means mu means that the job size is 1 over mu in expectation. Right? So let's see. So how often is a server busy if you have a MM1 system? So it's not hard to see that it will be about expected size over expected arrival time, right? So so this quantity, the load, will be very fundamental. So it's good to understand. So if I look at any sort of big interval of time t, how many jobs do I expect to arrive? About t times the expectation of a, right? Because each job is arriving roughly a units of time, and each job on average takes the expected size amount of service, right? So I expect my server to be busy sort of this fraction of the time, right? So this is the total time, and this is how much it's busy. So this will be expected size over the expected arrival time, which is just lambda over mu, right? Because EA was 1 over lambda, and this was 1 over mu. Good. And this quantity will be always denoted by rho, or the load of the system, right? And this will come up again and again in various ways. So it's good to have this definition here. Good. So again, just to sort of belabor on this point, if the arrival rate was 0.6 and the service rate was 1, so server can finish jobs at a faster rate, your load will be like 0.6. And we should always assume that the load is less than 1, because once the load is sort of more than 1, things sort of build up, right? Things don't get out as fast as they are arriving. So these things are not so interesting. Good. So once you have defined this MM1 setting, you can sort of see what we can do. So typically this leads to some Markov chain. So let's look at MM1 with the first come first serve or FIFO policy. Right? So when you are, say, running such a policy, there is a natural Markov chain associated with it, right? So the state here means how many jobs I have in my system. So if I'm currently in some state I, there is sort of lambda chance you go to I plus 1, or there is mu chance some job finishes and you go to I minus 1, right? So this is a, right, and it's Markovian, so it's a nice Markov chain. And once you have a nice Markov chain, you can do all kinds of things. You can compute what's the steady state probability of being in state I, which in this case turns out to be this expression where rho is again this load. Right, and once you have this steady state probabilities, you can, for example, compute the number of jobs in your system. So it's just the average number of jobs, right? Which again turns out to be this. And maybe this is a good expression to also remember for a MM1Q. So notice, say if your load was half, right, we expect about 1 job in the system to be there. And as this load sort of increases to 1, I mean, this number goes up, right, as you would expect. Right? Good. And in general, in queuing, one maybe studies more complex networks of these, right? You could have multiple servers and jobs feed from one queue to another queue and so on. And these things are very well understood. And you get more complex Markov chains that you can analyze. Good. So, okay, let's look at a more maybe general and interesting setting. And this is called MG1. So again, the first M is for Markovian arrivals. But now you have a G, and G is for general. So the job size distribution can be general now, right? So jobs don't need to have a Markovian or exponential service requirement. And so if you have this general distribution, we'll always denote the probability density function of this job by F. Right? So this will be our notation. So again, you can define, okay, what's the average size of a job? It's just the average. And you can define a service rate, which is 1 over the average size of a job, because this is how often the system will get jobs out of the system. But notice now this mu is not like a uniform rate, right, like in MM1, because yeah, it's a general distribution, so it's not a Markovian. So, but you can still talk of this mu. Good. Okay. So one thing is, so often this is a very good model in practice because you have this general distribution, and you might wonder, okay, this M may be a bit restrictive, but yeah, it's often a very good model because actually you can formally show that, you know, if you have many users, say, and sending jobs to a server, and these users are kind of independent and maybe they have their own distribution on how they generate jobs. But if you average this distribution or sum it up over all these various users, you tend to Poisson, right? So just like sort of central limit theorem, you tend to a Gaussian. For positive things, this tends to a Poisson. So usually it's a very good approximation in practice. So yeah, people study these a lot. But there are sort of more general models where you can look at G1 queues. And so typically things get hard here to get exact sort of analysis, and people look at all kinds of approximations and so on. So in this talk, we'll mostly focus on the MG1 setting. So any questions about the models? Okay, good. So again, we'll further restrict ourselves. We'll only look at one performance measure, which is the average flow time. So let me define what this is. So the setting we'll have is a single machine, and yep.
So just on the previous slide, I have one question. In the MG1, what information does the server know at any point in time? Does it know the distribution of the remaining? Does it use that the remaining job size to?
Okay, so we'll come to. So you can define a policy which is either blind, it doesn't do anything. Again, so it depends on your queuing policy, right? And actually, this will be a relevant question. We'll see several examples. Good. Exactly. So this is just a model. I haven't told you what's the policy, right? So the simplest policy would be, say, first come, first serve, but you could also do time sharing or round robin, so on. Yeah. So this is just sort of the input model in some sense. Okay, so we look at flow time. What is flow time? Just a quick reminder. So again, it's sort of the most natural metric you will think. So again, jobs are arriving over time. So these are the release times. And you have some schedule given by your scheduling policy. So the flow time of a job is just how much time it spends in the system. So when it completed minus its release time, right? So maybe just a quick picture. So you have these 3 jobs. So this is like the time axis. This length denotes the size of this job. So first this red job came. Maybe I scheduled it here. Then I started putting the green job. Maybe I interrupted this by this blue job and then completed the green. So the flow time of this green job would be this interval, right? Because it finishes here and it arrived there. And this is the response time, sojourn time, same things. Okay. So yeah, a very common objective is to minimize sort of the average flow time or total flow time of jobs, how much like each job had to wait on average. And so you can ask exactly as Kamesh was asking, okay, what's the right policy to execute jobs with, right? So if you want to minimize this objective. And you can have sort of various policies, last come first serve, shortest job first, shortest remaining time first, so on. And again, this is very well understood. So for the particular metric of total flow time, it's very well known, and probably everybody has seen this, that the optimum algorithm is shortest remaining processing time. So at any time, say you have several jobs to choose from, you just work on the job which will finish the earliest. Right? So maybe in this pic, yeah.
Can you assuming clairvoyant?
Yes, for now, yeah. Okay. We'll get, yeah. So we'll assume that the algorithm knows the job sizes, otherwise SRPT is not well defined. Right, so again, everybody understands this policy, just so here is an animation, I guess. Server is always working on the job that finishes the earliest. And one useful thing about when working with flow time is the following. So you can express the total flow time or the objective you care for. So one way is just the sum of flow time of all the jobs. And this other useful way is I can sum up over all times how many jobs are alive in the system. Okay. Right, or how many are unfinished. And why is this? So let's look at the proof. So imagine a job pays like $1 for every time step it's alive. Right? So the total payment a job will make, it's flow time. Right? So its jobs payment is just FJ by definition. So this is the total payment. But you can also count the payment in a different way. At each time step, how much payment is coming in the system, right? So that'll be exactly the number of jobs that are alive. So these two quantities must be the same. Good. So somehow, if you want to minimize the total flow time, you want to keep the number of jobs low. And sort of this is also one intuitive way to see why SRPT should be optimal. And again, one can also give other various proofs. So the classical proof is based on this interchange argument. Suppose you're not working on the shortest job, just sort of switch those two and you'll be better, right? So again, this is all sort of classic stuff. So I'll quick. So good. So if we look, what does competitive analysis have to say about sort of the simple total flow time minimization setting? It seems we know everything now, right? So we have just shown SRPT is one competitive. I mean, you can't hope for better. It's the optimal thing. And you can also show that, for various policies, first come, first serve, time sharing, I mean, you can come up with examples which show it's essentially as bad as it gets. So it's like almost omega n or n to the 1 minus epsilon competitive ratio. And notice this is sort of so n here is the total number of jobs in the instance. So, and this is as bad as you can get, right? Because if you have any algorithm that, is working as long as there is work to do, right? So if you have an algorithm that doesn't do anything even if there is work done, I mean, you don't want to do that, that's hopeless. But as long as there is a non-idling algorithm, it's always n competitive, right? And why is this? Because we just saw that flow time is just the sum of number of jobs alive at any time, right? So what's the best thing that can happen? Opt has one job, and we have n, right? So everybody is at least n competitive, and, right? So it seems the story is almost settled from a competitive analysis point of view. I mean, what's more to say? We could go home, but we'll see that actually no. So I mean, you can add richness to competitive analysis, and we'll see how you can cope up with these sort of very pessimistic analysis. Okay, and yeah.
Actually, it's possible that optimum is zero with positive one.
No, so if you're always working, that can't happen.
But if you have multiple machines, then you could
Yes. So I'm just looking at the single.
single machine.
Yeah.
Okay.
So we'll just look at So again, non-preemptive and single because So any other questions? Okay. So this was sort of what one says about competitive analysis. Let's look at things from a queuing point of view, and maybe I'll spend some time here because again these results might be new to many people. So let's look at the processor sharing or round robin, right? So here if you have 10 jobs, you work on them equally, give them 1/10 of the processor. Okay. So here one can show that if I look at say a job of size X that's arriving into my system, its average response time, right? So averaged over the whole sort of time horizon, right? So is X over 1 minus rho, and rho is again this load. You should maybe think of load as the rho as 0.9, right? So things are loaded 90% of the time. And okay, so this is a result in queuing that this is what it is, right? So maybe some notation. So Tx, I'll always denote sort of the response time of a job of size X. So expectation of Tx is the average response time of job X. Okay. So maybe one way, so the formal proof of this is a bit painful. I mean, it would need a whole lecture at least to do this. But But let's see one very heuristic argument. I mean, this is a wrong argument. So if some undergrad wrote it, you would give him a 0 on this. But still, it's maybe a good heuristic argument. So suppose there is a job of size X that enters the system, right? Now, we know like in the long run, the server is busy rho fraction of the time, right? I mean, this is the definition of a load. So typically this job will, get to work 1 minus rho fraction of the time, right? So it's about X over 1 minus rho. Okay. That's, right, okay, let's, right. No, okay, yeah. So maybe this is too heuristic. Okay, so once you have let's say we know this, you can then compute the average response time over all the jobs, which is just the expectation over all the jobs, and that comes out to be the average job size over 1 minus rho. Good. So a few things to notice here, maybe, so the point is this queuing result is telling you something about this processor sharing policy. It's giving you very fine-grained information. So for example, one thing you can glean from this is that the response time actually doesn't depend on this distribution G. It's pretty surprising. It just depends on the load. There is no dependence on this probability distribution F. Yeah.
Doesn't rho depend on the distribution?
Yes. So okay. So think of load as being fixed because I mean there has to be some dependence at least on something, right? But the point is, okay, we'll see an example for FIFO, for instance, where you could depend on the second moment of the distribution or some crazy thing, right? We'll see an example, yeah. But the point is, yeah, this just depends on the size of the job and just the load somehow. It's very, very clean and simple. It should be surprising. And also we can see from this that this is what you would expect, that process sharing is very fair, right? Because for every, if a job is twice as long, he waits twice as much on average, right? Which may not be a policy thing with other policies. So you can already sort of glean very fine-grained information from these things. Okay, so let's look at maybe another policy. First come, first serve. Again, PC. So let's derive, so we'll try to sort of maybe heuristically derive the expression for this. So let's say I'm a job of size X, I enter the system. What will be my response time or flow time under FIFO? So when you arrive, it's first come, first serve. So maybe you see some pending work before you, and then it's your size after that, right? Once your turn comes. So it's some maybe expected waiting time that you see before you, and then plus X. Now it turns out, so one can actually compute the expected waiting time. Turns out to be this expression, and S here is the size random variable, right? So E of X squared is the second moment of the job size. Okay. Now, good. So maybe this is so the response time would be like this expression plus X, and this is sort of very different from process sharing because there we just had X over 1 minus rho, right? Now, why this second moment comes? So we'll see this more formally in the next slide, but here is sort of one intuition. So actually, so this is kind of surprising, right? So it could be that your average job size is finite, some small amount, but maybe the distribution is so variable that the second moment is infinite. So what this is saying is that FIFO will have infinite average waiting time, right? So it's interesting, yeah. And one way to see this, at least intuitively, is that, so let's say your distribution of job size was that it's some large size m with probability 1 over m, right? Otherwise it's 1, right? So expected time is about 2, because this will have expectation 1 plus almost 1 from here. And let's say load is half, so things are arriving every 4 units of time. But in FIFO, notice, right? So whenever you have this one big job coming of size m, a lot of these guys, so think of a job like jobs coming every 4 seconds, just for concreteness. So all these guys will roughly be stuck for omega m time after this, right? So on average, a job will have omega m time, even though its average size is just 2. Right? So somehow, let's see why the second moment might come. And yeah, so let's make this a bit more precise. So actually, yeah, so let's maybe see how much queuing intuition people have so far. So imagine I'm at a bus stop, and a bus arrives, say according to a Poisson process with 10 minutes on average, right? So every 10 minutes I expect a bus to arrive, and it's following this exponential interarrival distribution. Now suppose I don't know the schedule of the bus and I just land randomly at the bus stop. How much do I expect to wait on average?
Not 5 minutes.
Okay. All right. So, okay, one answer could be 5 minutes. I mean, bus arrives every 10 minutes on average, so I arrive halfway maybe. Okay, so somebody who said 10, why 10? Okay, right. So you could also argue, so 10 could also be a right answer because it's Poisson process, it's memoryless, so I arrive. My arrival should have nothing to do with when the bus is going to come, it's memoryless, so maybe it's 10. And what's the right answer? I guess, yeah.
Something image.
Okay, that's good. Maybe should put a third bullet there. Yeah. So indeed, the 10 is the right answer, which might say, and this is actually this. It's called inspection paradox or length biasing. It's a sort of very counterintuitive phenomenon. Maybe when you first see it. So let's do this because I think Adam will need this quite a bit in his part. So let's do this more detail. So in general, suppose I have some random variable x, right, which is some distribution f, and let's say there is this process going on. So I have this time, and so something happens for x1 unit. So you are sampling x from this distribution. So maybe the first entry is x1. You wait for x1. Then the next is x2, x3, so forth. Now suppose, so think of these like as the bus arrival times, right? These are these intervals. Now suppose a person lands randomly during this interval, right? So think of this as a very long interval and you're landing randomly. So what's your expected time till the end of this particular sort of xi that you land in? That is the sort of problem clear. So this is called the excess of, how long till my epoch will end or how long it will take for the next bus to come.
Sum of the squares.
Okay, wow, you're quick. Yeah, indeed. Good. So, right. Can you find the distribution of that? Okay. So, yeah, so this is called the residual x. This is all exactly what we are doing here. And yeah, this is a very fundamental quantity in queuing. And let's do the proof that Yossi probably had. Right. So maybe, so here is a proof by picture. So think of this process as, again, I'm here. When this one comes, I sort of go up by x1, and there's this interval finishes, right? Then the next one starts at x2, then it sort of finishes, and so on. Now, if I land up randomly, so the way I have drawn it this way is because if I land up randomly, what I see as remaining is exactly the height of this thing, right? So if I land in the beginning of this interval, I'll see x2. If I land here, so on. Right. So the average, so I'm landing randomly. So you can convince yourself the average will just be the area of this thing, right? But these are sort of 45-degree lines. So if this is x2 height, this is also x2 base. So, right. Okay, so the average will exactly be sort of this. So at least you should see why the second moment should come in. And in general, if you play around with this more, you can actually compute the exact distribution of this random variable xe, which has some form, which I guess Adam will use. Good. So, okay, so most people got this intuition correct, so except Mohammed, maybe. Okay, good. All right. So let's look at something more complicated, the SRPT policy, which we know was one competitive, right? And it's maybe good to spend some time to understand what queuing says here, and we'll look at SRPT in more detail sort of for the rest of the talk. Right. So if you look at a queuing book, you see this sort of, so again, this means expected response time for a job of size x. Right, and now it's sort of not the easiest expression to look at. And I've already I could make it look more ugly by, so this row of x is actually this quantity, which is the load of jobs of size less than equal to x, right? So this is sort of the average size of jobs less than equal to x. And remember, load was, okay, so maybe also write load as lambda times. So this would be the total load, but if I was looking at load made up of jobs of size less than x, then it would be exactly that expression, right? Because this is the average size of jobs less than x times lambda. Okay. Right, so this is rho x. So it's some mess. So let's try to make sense of this, what's going on here, right? So at least everybody should be able to, even if you don't know queuing, we should be able to follow how we could have derived this, at least heuristically, or some definition of heuristic. So again, think of you're a job of size x, you arrive in the system. So what will happen? So this term will actually correspond to the waiting time. Maybe there is some stuff before me of size less than x that has to finish. And then maybe I'll start executing. Maybe I get interrupted by new smaller jobs coming in, so on. So this is what I'll call the extra time. So this is like how much I wait to just get started. And this is the extra time until I actually finish. And let's kind of see what's going on. So indeed, yeah. So if you're a job of size X and you're doing SRPT, right? So small jobs sort of get first. So how much will you wait? So you look at, okay, what are the jobs of size X before me? And from kind of this FIFO analysis or this length paradox, something like this. So if you remember again, FIFO, it was lambda times the second moment of job here divided by 1 minus rho, right? But now I'm only looking at jobs of size less than X. So sort of, this would be sort of intuitively the right thing to look at, right? So you would expect, so rho becomes rho X because I only care about jobs of size less than X, and this is sort of some right truncation. So maybe it's easy to believe that, okay, so let's say this is the workload I see before me in steady state. Good. And actually, if we expand this expression out, it will exactly be this numerator, but let's not do that. Now, this is the workload I see before me, so I'll wait for that. But notice here I have a square in the denominator, and here I don't. So can anybody see? Okay, so maybe this is just, yeah. So I come in the system, I see pending work less than X. But yeah, the pending work is this, and here I have a square. So does anybody see why I have the square there?
Because the loading is rho and you have 1 minus rho.
Okay.
The loading is rho and you have 1 minus rho.
Okay, good. So, right. So it's good to again see. Right. So when this job came, he expects to see about this much work ahead of him. But notice while he's waiting, still more work of size less than X is coming in. Right? At rate actually 1 minus rho of X, the load kind of these small jobs. Right? So this sort of pile in some sense is decreasing only at rate 1 minus rho of X. So you get this additional, right? So sort of this is leaking only slowly because new stuff is filling in at rate rho of X. Okay, so this is the waiting time. I mean, this argument can be made rigorous. Didn't hand wave too much. And now let's look at the extra time. So yeah, once a job starts executing, its size will start falling from X all the way down to 0. Now let's do a thought experiment. If this job is of size T, it has still T units left, at what rate is he getting out of the system? So again, new stuff might interrupt him, right? Stuff which is less than T, because he's currently of size T. And that stuff is roughly coming at rate rho T. So he's getting 1 minus rho T share. And so somehow seems at least intuitively the right thing to do, right? So even though these things sort of look maybe formidable, I mean, sort of there is some sense to these. Good. Okay, and this is probably one of the hardest formulas I know in queuing. So if you understand this, like you're in a good shape. Okay. So good. So this was the thing for a job of size X. And so if I want the average response time, I can take average over all X. So that would be the average response time. Now notice, so if I take another average, you will get yet another integral outside. So it's not easy to make sense of it, right? It's not. So for example, this insight that SRPT was optimum, which in a combinatorial way was very easy to see by interchange argument. I mean, here, how do you make sense that for any distribution F, this is better than any other scheduling policy? So sometimes, yeah, it's not really easy. Good. Okay, capital F is the cumulative distribution function of F. Sorry.
If you plug specific distribution.
Exactly. So you would get a number, yeah, which is exactly the size you, yeah. So yeah, queuing would give you this very refined information for every distribution what you can expect. But the point is, yeah, so it's giving you this great thing on one hand, but on one hand, maybe it's hard to argue about, right? So again, it's very different from maybe comparative analysis where we have a different focus. And so let's see, but you can still sort of, yeah.
So just, just trying to make sense of this thing. If we plug in and make this an MM1 SRPT, does it make sense?
Okay, so.
Sorry to put you on the spot.
No, indeed, yeah. So I don't know. So maybe things will cancel out after a lot of work. Yeah, maybe not even. No? Okay, no, actually, yeah. No, I'll talk about this. Good. No, it doesn't make sense. And actually, I'll come to MM1 SRPT. Good, yes. Right.
So there's also Little's law, right?
Yeah.
Does that follow, or
Are these results consistent with that, or does that only have to work in a certain scenario?
No, so Little's law is something very, very basic. It just says you can relate the number of jobs in the system with how much time it spends, right? So
Can you use these results to derive something similar?
yeah, so you can use, for example, the time a job of size X spends to figure out in steady state how many number of jobs of size X I'll have in the system. But that's all Little law does. It just relates number of jobs to time.
Yeah.
Returning to an question, if what is better, MM1 FIFO or MM1 SRPT?
SRPT, because SRPT is always optimum.
So for deterministic, they should match.
Yeah, maybe not. Okay, Adam is shaking.
Deterministic, they should match. They're all the same size, so maybe first one.
Blind palaces match, not SRPT. SRPT is still better.
First come first.
MD1.
Oh, MD1. Sorry, I thought you said MD1. Yeah, MD1, you're right, yeah. And
Does it? Okay.
MD1.
All right. The queuing experts can figure it out. Yeah, I don't see. But actually, this MM1, we'll come to this actually.
So if I made this GG1, how would these expressions change?
Okay. So for GG1, you can't get an exact expression, and people do all kinds of approximation. And actually, I'm not the expert on this, so maybe you should ask Adam or many queuing experts here. So this is sort of beyond what I even understand in queuing. There is no good expression for GG1, exact expression. Any other questions? Good. Okay, so let's still try to make some connections because that's what the tutorial is about. Okay, so let's maybe ask one question. In queuing, we are deriving all these expressions, how things degrade as a function of load and maybe the expression. And we saw a few things, FIFO, process sharing. Least come first serve is also similar, though I didn't prove this. Right, so notice, if I just look at it as a function of load, what's happening, there seems to be this 1 over 1 minus rho degradation, right? As your load approaches 1, this is, and if I keep the other parameters, let's say fixed. So now this is how the system is degrading. Now you can ask, this seems to pop up all over the place. So is this fundamentally inherent? And surprisingly, this, at least as far as I know, wasn't really systematically studied. And so I noticed about 10 years ago that if you look at MM1 SRPT, and this is what Anupam and Cassius you were asking, actually you get this funny thing. So again, this expression is what time sharing would do, expected size over 1 minus rho. So just a very small loss here, but you improve by this log factor, E of, so log of roughly 1 over 1 minus rho, right? So at least it's showing maybe 1 over 1 minus rho dependence is not completely fundamental. Sometimes you can have a different sort of degradation of behavior. And it's interesting because if you look at any blind policy or non-clairvoyant policy or something that does not use sizes like SRPT in its scheduling decision, so like first come first, so all these are blind policies, right? Like time sharing, you don't really need to know the size of a job. You just equally give them the processor. Right? So if you don't use policy, so all of them would have such a dependence in MM1. And why is this? So do people see why? Follow from something we have seen. So any blind policy that does not use a size should have this. So if a policy is not using the size, it's just working on some jobs, right? Like at rate 1. And then, so remember we saw this Markov chain in the beginning for MM1, like things move one step forward with rate lambda and back with rate mu. So all these policies will have the same Markov chain because you are just working at rate. All the jobs look the same, basically, right? So there is no difference. I mean, it's MM1, it's memoryless. You're not looking at the size. So no matter what you work on, there is rate mu, it finishes. So it's exactly this. So good. So SRPT is telling you have this sort of improvement if you have sort of the knowledge of size. So you can call this sort of the price of non-clairvoyance in this MM1 setting, this improvement. Okay, so this proof, again, this MM1 SRPT formula is a complete mess, right? And even for MM1, this was quite painful to derive. So you might ask, okay, why did I do it? So there was no apparent reason, but it was motivated, right? So So there was some connection to competitive analysis that we'll see, and that sort of suggested that there might be precisely this improvement, and so there was sort of reason to really persist and try to sort of simplify that thing and get this. And we'll see this connection later, right, once we see connection to competitive analysis. Okay, but still you can ask, okay, there is this small log improvement, but I mean, who cares, right? So it's, you are get this 1 minus rho degradation anyway, there is this small log improvement, it's negligible. So, okay, you can say that blind and SRPT are almost the same for MM1. So, okay, maybe not so good news. But here is maybe a more surprising fact. So if you look at MG1 now, if you allow general distributions for job sizes instead of exponential, somehow things can go where it's sort of, it's a very surprising result, I think, that if you look at the average response time, so okay, so there is a certain distribution called the Pareto distribution, which is a classic heavy tail distribution where, so in exponential, the tail sort of drops exponentially. The probability you're bigger than size x is e to the minus x, but suppose you only drop polynomially. And this exponent of the polynomial is, let's say, between 1 and 2. This is called Pareto alpha. So for this distribution, actually you can show that SRPT has an amazing degradation with load. So if your load is approaching 1, this performance will very, very slowly degrade. Right? It's log here instead of same time. Say if you look at processor sharing instead, you had just 1 over 1 minus rho. So it's exponentially better than processor sharing. So what's going on? I mean, this is really a big improvement we can't sort of ignore. But turns out actually here, for this particular distribution, there is another policy, a blind policy called shortest elapsed time first. And maybe I'll first show this cartoon what this policy is. So it's exactly what it says. So let's say, so at any time it's working on the job. So it doesn't know the size of jobs, it's blind. It's working on the job which has received the least amount of processing so far. It's kind of the opposite of SRPT. Like you work on the job where you have worked the least. So say here's a cartoon. So if a job arrives, this is the only job, you start working on it. So maybe you're here. Then this new job arrives. So now this is the job where I haven't worked at all. So I'll start working on this job until it catches up with this. Now maybe these two jobs are there. So I work on them equally because both are sort of, if I work on this a bit, then he's the least and so on. So I'll time share. But then maybe a new job arrives and then I start working on him until he reaches here and so on. Right? So it's again blind. And here it turns out, if you just do a computation, it's a bit of a mess, but you can do it. So for this Pareto distribution, they almost match up to constant factors. Okay. As opposed to process sharing, which is exponentially worse than SRPT. Good. So then this leads to a natural question. Okay, I mean, for any distribution G, is there always a blind policy that's maybe close or roughly close to SRPT? If not, how big can the gap be, and so on? Okay. So here is a result that we showed a few years ago, that for any GG1 system, so ignore the G if you don't like it, that no matter what distribution of job size you have, there's always a best blind policy which is within sort of a log factor of SRPT, right? So it's pretty close. Assuming some technical condition that the second or 2 plus epsilonth moment of the job size is finite. And surprisingly, these results come from competitive analysis. So let me try to give a connection. So what's going on? Good. So maybe in the next couple of slides, let's see what competitive analysis has to say about such blind policies. Right?
Just quick question.
Yeah.
So you assume 2 plus epsilon moment, but for the Pareto you didn't have that. So how?
Okay, good. So our result won't apply for that setting, right? So there we, So probably it's also just an artifact of our proof analysis, right? So for Pareto, I cannot use directly this.
Is that policy computable easily?
Yes, it is. We'll see what that policy is actually. Okay. Oh, I see. So precisely the best will not be. It's not clear how to characterize it, but we can always find one policy which is always within log of this. Okay. So let's take a bit of a detour on competitive analysis of blind policies. So again, there is, you're in the blind setting, right? You don't know the job sizes and you're comparing with SRPT, which sort of is the ultimate thing. So it's not a surprise that any policy must do bad. In fact, by more clever analysis, you can also push this to almost omega n. But okay, so this is bad news. And let's see how these lower bounds are constructed, right? So even for specific policies, I mean, if you look at time sharing, there is a bad example which looks like this. So you give 2 jobs in the beginning of size 1, then maybe at time 1 you give another job of size half and so on. So in this case, like SRPT would just maybe delay this job and just finish these guys as they come, and it has like 2 jobs on average remaining. But you can see that process sharing just like keeps piling on and never finishes anything, right? So that's why it's sort of n-competitive. Similarly, shortest elapsed time first can go wrong in the competitive analysis sense, because we are looking at the worst case input, right? So you get a job of size 1, and just when this was about to complete, adversary gave another job, right? Just when this was about to be done, he gave another job, and so on. So SETF will not get rid of any of these jobs. You have almost n jobs in the system, and SRPT, of course, could just sort of do them, right, and just have 1 or 2 jobs in the system, right? So that's why they are all omega n competitive. So this is not saying really anything interesting, right? So competitive, the notion seems too sort of pessimistic to give any good insight. So yeah, so we need to sort of overcome this pessimistic behavior, and so there are several ways of doing this, smoothie analysis and so on. Here is one way. It's called resource augmentation, which is quite common in scheduling. So Kalyana Sundaram and Proust had this very nice paper where they said, let's do this thing where let's give the online a slight advantage over the offline algorithm, right? And by giving it a slightly faster server, let's say by like 1 plus epsilon. So again, online you're giving extra power, but you're comparing its performance to a server which has still the speed 1 processor, right? So then it turns out, so this is called resource augmentation, and you can prove sort of very nice results in this setting. And this kind of also has an intuitive connection, right? Because if you can show that, okay, so let's see actually what we know. So for instance, one result you can show is that SETF is 1 plus epsilon speed, 1 over epsilon competitive. Okay, so if you give it just ever so slightly faster processor, then sort of this bad example that we saw dies away, right? And in this picture, it would make sense, because if I give it a slightly faster processor, it wouldn't suffer from this, right? It would actually finish this job before this guy came. It has a slightly faster processor. And again, sort of the analysis is not too hard. You can sort of make this intuition precise and show this. But interestingly, it turns out for processor sharing, you can construct bad instances where even with like speed up 2, you're omega n competitive, right? So that really takes a long time to sort of, and somehow maybe this is giving one distinction between PS and SETF. So we saw like in the queuing world, you get this fine distinction, right? Like for Pareto distribution, SETF had this logarithmic growth with load, PS was linear growth with load. And so maybe this is sort of one way to reconcile these things. So the point is, yeah, often resource augmentation can give also very nice qualitative information about such things. Good. Right. So yeah. So now, let's try to work towards how we prove this result about the one that there is always a good blind policy close to SRPT. So quickly, some things. So if we have so in competitive analysis, you can also look at a randomized algorithm. And maybe I should define this because it's a bit different from the queuing setting, right? So queuing, there is randomness on the input, but in the competitive analysis world, again, so the input is kind of worst case, but you only have some external randomness, right? You toss coins and do something. And then your algorithm still, so you can define a randomized competitive ratio as worst case over all inputs, but sort of now the expected cost of your algorithm over op divided by best offline, right? So again, standard competitive ratio. And here it turns out that if you allow randomized policies, there is a very good blind policy, right? So we saw that if it's a deterministic policy like time sharing or whatever, they are all bad, at least omega of cube root of n. But if you allow randomization, you can design a very good algorithm which is log n competitive. And this algorithm is actually sort of just a discrete variant of this shortest elapsed times first. So let me maybe quickly describe this. So imagine, so shortest elapsed times first always works on this job that's like the most new, right? It has the least amount and okay. So you can think of it as, let's say there are many sort of queues. This is with threshold 2, 4, 8, and so on. So first all jobs enter here. Once like every job here has received 2 units, either it completes or let's say it goes here. So if you're always working on the lowest queue, if it's non-empty, it's kind of like SETF, right? A discrete variant. Okay. So again, if you just have these discrete thresholds, it will be bad. It's a deterministic algorithm. But their idea was that if you, for any job J, let's say for class I, if you choose a random threshold, So instead of 2 to the I, you add some exponentially truncated noise of like about 2 to the I over log n sort of mean. Then actually you kill that bad example, right? Because now for adversary, there is no way to, so again, the bad instance is sort of, this job is almost done, but it doesn't quite finish, right? But now if you sort of randomize these thresholds, you don't have this problem, because if a job is not finished, most likely it also has a lot of work remaining on it, and somehow you can relate SRPT to this. So using this sort of very nice analysis, they showed there is a log n competitive randomized algorithm, and then this was extended to sort of the multiple machine case by Becchetti and Leonardi. And yeah, you get a log n instead of this deterministic thing. So let's see how we use this. Okay, actually, yeah, before I do that, so a couple of things. So this log n is also the best possible. So one can give a lower bound on the randomized competitive ratio of any algorithm. So RMLF is really optimal. And sort of I want to say this gap that we saw between MM1 SRPT and let's say MM1 process sharing. Right, so here it was. And here we had this log improvement. So this was kind of motivated by this result because, so let's do a following thought experiment. Right. Okay, so there is a tight log n lower bound for sort of any randomized algorithm. And how does that lower bound go? So it's something like this. So suppose you have n jobs at time 0 which arrive, and they have exponential job size with mean 1. Right? Now let's look at time n minus some small, like n to the 0.99, right? So what would I expect? So you would expect about n to the 0.99 jobs. Each job is of size 1, right? So you'd expect this many jobs to remain. And in blind, exactly these many jobs, say up to plus minus root n, would remain because it's kind of memoryless, right? So it has these, there is still this much time to go until you are in n, and right, so each job could finish within one time step because of memoryless property. So you'll have this. But opt, if it's doing SRPT, it will only sort of retain the large jobs, right? And the last n to the 0.99 jobs are kind of size log n because it's exponential distribution, right? So opt will have much less jobs. So you get sort of this log n improvement between these things. So this kind of suggests that maybe if you have MM1 SRPT, like in steady state, it might retain only these bigger jobs. So this log n would somehow should translate to this, because n is the number of jobs in the queuing system, which was like 1 over 1 minus rho. Right? So this was sort of one way for reason for going through that calculation, and indeed it worked. Right. So how do we show this more generally? Right. So again, this is this theorem to remind you that there is always a bias blind policy within this of opt. Okay. So the idea is to sort of relate this worst case and average case using, say, Yau's minimax lemma. Right. And actually, we just need the weaker direction. So let's go over this. So what is a queuing system? You can think of it as giving you a distribution over sort of a lot of instances, right? So if I have some, say, MG1 or GG1 queuing system, so what is it? Some jobs are arriving. So if I plot the workload, pending workload, so this graph is independent of the queuing policy, right? Because if you're always working, this is a fixed workload, and then the server is empty, everything is finished, then there is maybe a new, what's called a busy period, and so on. So you can think of a queuing thing as giving you sort of these instances with some distribution given by the GG1 or whatever. Okay, now Yau's lemma says that, okay, now if you have a distribution on input instances, there is always a good deterministic algorithm which is not too bad compared to opt, right? Its competitive ratio is within the best randomized. Okay, so again, maybe those of you have seen this, it's obvious, but maybe let me not do this. So you can sort of bound this, right? And this we know for RMLF is log n, right? So this would suggest that if I look at the best blind policy, so if these, let's say, things were of size n, these busy periods, you should be within log n of SRPT, right? Good. Okay, so this suggests that if these things were of size n, but what is n for a GG1 system? So we need to understand what is the number of jobs here. But we kind of understand that. You can show that, okay, number of jobs in a busy period is roughly this. So this would suggest that, okay, so best blind policy should be within log of this thing, right? So instead of n, I just plug this. Okay, so this almost works, but there is a slight problem. You need to do more work. and maybe this needs a while to see. So the point is, right, so on average, a busy period has like n jobs in it, which is this. But it could be that all sort of, there is this positive correlation going on, right? So big busy periods affect you much more disproportionately, right? So imagine like, right, there were a lot of fake busy periods of size 0. I mean, that would have no effect, but that will bring down the mean number of jobs in a busy period. So you get a much sort of higher pain from sort of bigger busy periods because they have more jobs, they are delayed more, so on. So you need to sort of understand this correlation. So sort of we do the natural thing. So, we pick some threshold n naught, which is, let's say, much bigger than the mean number of jobs in a busy period, which is like 1 over 1 minus rho. So think of C as like 1 over epsilon. So for busy periods with like less than n naught jobs, life is good, right? We are within log n naught factor, which is log of 1 minus 1 over rho. And now we just want to say that these big busy periods don't affect you too much. So natural ways to bound their contribution is just that you look at all these big busy periods. The worst contribution then they can make is like the length of this busy period times the number of jobs that were there in the busy period, because maybe each job is delayed by that length. Okay, but these things are maybe complicated random variables correlated in weird ways. So, but to understand that, we can sort of decouple them via Holder's inequality, and then it sort of boils down to just estimating these moments a few times, and sort of one does some analysis and things fall out. Right, so indeed, so the point is just morally, like this is the right number of jobs. You have to be a bit careful about sort of these long things. Good, so in some sense, we related worst case to average case via Yau's minimax theorem, and sort of gets some interesting insights. So again, one immediate open question in this area is how do you extend this to multiple machines, right? And the problem is somehow now these busy periods and all are not uniquely defined. It depends on how you schedule jobs and so on. Even though RMLF is still polylog competitive, so morally you should expect things don't change, but it's not at least immediately clear how to push this framework. And maybe just 1 minute on, say, possible other quick connections. So there are sort of, have been few attempts to connect queuing and maybe more adversarial insights. So there was one very nice paper, again, almost 20 years ago by Kleinberg et al., where they defined a notion of adversarial queuing theory, right? So they try to sort of take this notion of load from queuing theory, but sort of extend it in an adversarial sense. So in any window, on average, you have load rho, but things could be adversarial. They sort of prove nice results. So that's one way, and maybe this hasn't been explored as much as it could. There's also smoothed analysis, which sort of in the similar flavor, stochastic and worst case. And there have been a few results on this. One thing I think could be very interesting is trying to design new algorithms which kind of combine the best of online and offline, right? So, and maybe Adam will talk a bit about this. So, for example, a self-tuning algorithm, if your input was really worst case, okay, you're no worse than the competitive ratio, but if your input had some pattern or some nice distribution, then you should automatically converge to the best queuing thing and so on. Right? So, and presumably using, say, learning techniques, one could do this. One could also sort of, there hasn't been much work in online algorithms on networks of servers, which have been studied in queuing a lot. So it's one direction. And maybe another thing is, so in online, people use potential functions a lot for analysis, which I didn't talk about, but it's a very common technique. And in queuing, people call these things Lyapunov functions, which really are the same thing. And maybe it's often, sort of there are very clever constructions of these things. And maybe there could be sort of more synergy trying to use idea from one to the other. And with that, let me stop. Thank you.
We'll take a couple of questions.
Just a comment that this 2 plus epsilon, I have seen also Lyapunov functions that might be inherited in the process.
Yeah, so I mean, we get it because, we do this holders thing. Yeah, so it could be for technical reasons.
It's also there. The question is also, so do you have any null bounds, or do you know any distribution where you cannot do constant?
No, so SRPT, the MM1, right? There was this log gap. So it's tight in some sense, right? Because blind in MM1 always has this 1 minus rho, but we saw in SRPT. Is that the question? Or?
Where you cannot do constant?
Yeah, because there is actually this log. I mean, there is one distribution, in particular the exponential, where you have this log gap.
So what are the type of results that exist for worst case scenarios. So the idea is, instead of working the expectation, try to estimate the real behavior of.
Okay, so Adam will talk much more about the tails and so on. Yeah, so wait for part 2.
Nikhil again.